right, good evening everyone, and welcome to the November meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. We've got quite a packed program for you tonight, and it'll be a fantastic program. We're going to start with some of our usual stuff, Ottawa skies, from Dave Chisholm. David Lauzon will be giving us an update on the Fred Lossing Observatory. There have been some excellent developments there, some improvements to the site. I'll let David talk about that. Paul Klauninger will be taking us through a project that he's named the Dragon Quest, which will be pretty interesting. And then after the break, we've got our guest speaker Ben Gerard, who will be giving us a talk on imaging worlds beyond our solar system. And we'll close off the meeting with observations, the observing challenge, announcements, etc. All right, so these are our new members in this past month. Welcome Susie Junot, Christopher Landry, Marcus Leach, and Carol McCurry. So that makes for 50 new members in 2018. Yes, and this just came from the national office. Governor General Julie Payette has officially become the patron of the RASC. So they were doing, the Governor General was doing a review of all of the charities and organizations that she was a patron of, and it looks like the RASC has officially been selected to continue under that patronage. So that's good for the society. All right, members in the news. Yes, we are awarding our first of the Explore the Universe certificates. So congratulations, Murray Campbell of the Ottawa Centre. I don't know if you're here with us today. I've got your certificate here. So it's great. We finally have a member that's taken the initiative and has gotten himself that certificate. Congratulations again, and I hope we get many more Ottawa Centre members pursuing the various certificates that the Society has. All right. Is Mr. Tim Cole in the house? No? Nope. All right. So the annual general meeting of the Ottawa Centre will be held as part of the monthly meeting on December 7th, 2018. Notice will be sent to all members via email and will be published on our website. The annual general meeting is where the club executes its official business in terms of elections and reports of the various officers. So that will take about 30 minutes of our meeting in December. Gordon, are you here? I'm here. Can you come give a little spiel? You've got two slides there. Your clicker.
Left one?
Right.
Right one. Yeah, that right. Good evening. Okay, so at the annual general meeting, we have to elect all the members of council, and currently, everybody is acclaimed, but I'm accepting nominations for any of the positions. We do have an opening for meeting chair. Oscar, now that he's married, is finding it takes a little more time than he's allowed. And so if anybody wants to nominate someone, or if anyone wants to step forward, please do so. What else do we have here? Okay, so nominations can be submitted for any position. Nominees must be members in good standing. They have to be at least 21 to be a national representative. And the nominations have to be supported by 2 members, sent to the secretary, which is Chris Tarrant, before 8 o'clock on December 2nd. Is December 2nd the next meeting?
That's 5 days prior to the next meeting.
There we go. Yeah, because that's what I thought. Meeting's on the 9th. 8th?
7th.
7th. Get there eventually. Okay, and just email it to secretary@ottawa.rasc.ca. We have an opening for light pollution, light abatement, and we have another one for, National Council.
That was on the first thing.
That's right, it was. Okay, so that's it. Okay, thank you.
Alrighty. Thank you, Gordon. And I do hope that some folks do step forward for some of those roles. It's a great way to get involved in the governance of the society and to get involved and sort of steer the direction that we take the club. All right. And I'm still looking for submissions for the 2018 Paul Commission Observer of the Year Award. So be sure to send me your logbooks or sketches, photographs, anything that encompasses observations before the November 25th deadline. You can send it to me via email. I know it's not here, but it is meetingchair@ottawa.rasc.ca. All right, and I'll hand it over to Dave for Ottawa Skies for November.
I love that this screen is working properly here now. It makes it so much easier. Okay, so let's take a look at the moon phases for November. The full moon is going to be on November the 23rd. As you're all probably aware, we're switching to standard time on the 4th, Sunday. I wish we would stay on standard time. We could get our observing in an hour earlier year-round. We got Comet 46P Wirtanen. This shows where it is from November 15th onwards. It's pretty low in the sky, but something maybe you can try for. We have 2 meteor showers this month. The first one is the Torrens meteor shower. It peaks on Monday night. This is a long-running meteor shower. It only produces, though, 5 to 10 meteors per hour. It's unusual that it consists of 2 separate streams. First is produced by dust grains left behind by asteroid 2004 TG10. The second stream is produced by debris left behind by comet 2P Encke. The show runs annually from September 7th to December 10th, and as I said, it peaks on Monday night. Best time to view it is after midnight, after the moon sets. The next one is the Leonids meteor shower. It peaks on November 17th and 18th. This shower is unique in that it has a cyclonic period of about every 33 years where hundreds of meteors per hour can be seen. Unfortunately, this is not the peak. The last peak was in 2001. The Leonids are produced by dust grains left behind by the comet Tempel-Tuttle, which was discovered in 1865. And as I said, it peaks on the 17th overnight. The 18th best viewing time is after midnight. Most of the time I say Mercury is not visible. It is this month. Greatest eastern elongation, that means it's the furthest away from the sun on November the 6th, and you can see it just after sunset in the western sky. Venus is visible in the early morning, last half of the month, and Mars is visible in the first part of the evening. Jupiter is not visible. Saturn is visible the first part of the evening. It's setting very early right now, so this will be your last opportunity to grab it in the next couple of weeks. Uranus is visible all night, as is Neptune. And speaking of Uranus, here's a cartoon. Thank you.
Uranus hurts. All right. Thank you, Dave. And I'll be sure to mark that Leonid shower in the year 2034 in my calendar. All right. David's going to come up and give us an update on the FLO. Another David.
This is to all the Daves I know. This is to all the Daves I know. There have been many developments with FLO in the last little while. Many changes, such as we're setting up a new observatory. We're expanding the mound, and trees have been cut. Now, before I begin, there's another little change that people need to know about. The outhouse has been moved, so you'll have to skip to the loo a little bit further this time around. And let's right-click There we go. This is a picture I've shown before, but what I really want you to see is the trees up around here, and there's the outhouse as a reference point, because that's where the new observatory is going to be placed. That's what it looks like right now. So if I can go back, you can see that a little bit of work has been done in this area. And that's what did it. So we had contracted a backhoe operator to come in and to clear this area. Speaking with Gordon and Chris that were there, and Rick that were, actually, was Rick there that? Yes, Rick was there that day. I was contemplating trying to go in there with a chainsaw and clippers. I'd still be there. This guy did this work in maybe 2 hours. You'll see as this progresses just how amazing this new site's going to be. So once again, this is what it looks like, and there's just a few things I wanted to point out to you here. Yes, the loo has been moved from here to here, so just be careful that there is a little tree in the way for privacy's sake. There is now a ramp that goes up here. This used to be, I thought it was a fence line at one point, but back over here, and I'll show you this area in another little bit, it's actually glacial cross bedding, and you can actually see the bedding of the rock. So this is actually part of a glacial moraine or an esker that was here long beforehand. The farmers that used to farm this field, and this was a farmer's field before, piled up rocks in this area, but I didn't realize that this is actually a natural feature. So if you're out there, check back over here, and I'll show you this a little bit later. And there's some absolutely wonderful geological features there. So here's just another view showing what it looks like from the warm room. And this pad, just for scale, this pad is about 15 feet by 15 feet. So, oh, it looks like there might, another observatory could someday go there. Just a thought. These rocks that you see right here were leftovers from when the excavator, or from the backhoe cleaning the whole area out. And you should thank Chris Tarrant for basically making that whole thing almost himself. That was a little pet rock project that he had, and did a very good job on that. We will eventually have some type of a guardrail along here so that people don't trip over that in the middle of the night. The Inukshuk. There's an Inukshuk right here too. And I think that someone built that, someone's little daughter. But we're going to keep that to ourselves for now. What's that? It wasn't you. No. Oh, yeah, that's right. We had some visitors come out, and one of the neighbors built a little Inukshuk there. So, very cool. Where our work came in was once this was piled up here, and the backhoe operator did an absolutely incredible job with laying out the stone, was for us to level it out, and all these little branches that were sticking up over here and all around there, they had to be dug up by hand. So there was quite a bit of our physical labor that had to go into this. And one of the reasons why I wanted to show you this shot too is, take a look right through here. That's almost due south from the mound. The trees were right up to here at one point. But we'll show you a better picture of that a little bit later on. So this is not what we're building. This is what we're building. This is very similar to the one that we're going to be building. This is Oscar's observatory. And the reason we were bringing up this picture here is that this deck is the next stage for the observatory. There were literally a song and a dance that we had to go through to get permission to build this. That's a story for another day. It's all good. We have friends in very high places. And this deck is going to be, I think, the next major work project for the observatory. We're hoping to do this sooner than later. We would like to have the observatory up before wintertime. However, with the way winter's coming this year, it's a wait and see thing. So this is a sky pod. It's 2.2 meters in diameter. and a 14-inch Casagrain is going to be put in there. So that's eventually what's going to be going into that observatory.
Can you give us the cost of something like that?
$1 million. No, I have no idea. I can't say for sure. The costs are still being compiled, but this is the Sky Shed Observatory that we bought secondhand, and Chris, correct me or Gordon, correct me if I'm wrong. It was 1,500-ish.
1,700 for the dome. It'll be about 1,000 for the deck and about 1,000 for all the backhoe work.
So for literally $3,000-ish, we have an observatory class observatory. Like seriously, it's the work that can be done with the 14-inch Schmidt. We can be doing professional work.
And the 14-inch was a donation.
So life is very, very good. Right now, we're looking at having it on tripod mount, I believe, until we get things sorted out with that. We're still in the planning stages, I believe. Yes? Yes.
Tripod mount initially. You can always upgrade it with gear.
Yeah. The tripod mount, if I can just go back here, would most likely fit through a hole in here so that the vibrations won't bounce it up and down. So it'll be fairly sturdy. Okay, and this is the Sky Shed that we're going to be putting in, and here we have this here just for scale. That 2 people and a big scope, cozy. More than that, very cozy.
Those extensions are just storage space?
Yes, when these areas right on here, and I think there's 3 of them, 3 or 4 of them. 3. Your computer will fit in here with a little slide out shelf. Equipment can be stored over here and over here as well. I've been looking into buying one for myself, and I just can't picture my equipment being in there without the bays. You absolutely need the bays to be doing any work, or you're going to be trugging stuff all over the place. With the scope that's coming in, right now there's no power going to it right now. So a battery will have to be kept in the warm room and then brought out to run your equipment. Ideally, what we would like to do, oops, I don't know what happened there. There we go. Ideally, what I'd like to see happen is conduit run out there with power. We're still at the looking at it stage. Okay. The loo has been moved, so yes, you will have to skip to the loo a little bit further. And just with the outhouse, we will be fitting in a tank for it. Right now, there's a hole, and we will be filling that with, replacing that with a tank. The mound. This is the second thing that we were looking at doing this day. The mound, for those that don't know, actually, if you take a look at the screen, that's about the actual size of the mound. We wanted to increase that because we're really trying to encourage people going out and using the observatory. So we've actually increased the mound by about 3 times. And it was literally a work of art watching our contractor here with the backhoe. You couldn't have even done it that neatly with a shovel in hand. This guy was absolutely incredible, the way he was just manipulating all the controls, literally just like this, absolutely incredible. And we're waiting for this to settle right now. So when this does settle, we will be putting down some topsoil and seeding that so that it'll just be a natural extension of the mound. These trees over here might accidentally disappear someday, next time the backhoe operator comes in. But anyways, they are a bit of a nuisance when looking at the southwestern sky. They will be moved. And since I've got this picture up here, the trees over here, a lot of them have already been removed. I haven't been out there since they were supposed to come in the second time. But this is phase 1. Hopefully this will be phase 2. Way back here, and you can't see it from this picture, there's a butternut tree. Does anyone know the problem with having a butternut tree there? It's a threatened species. So it will never be moved. And that's fine. It's low enough that it's not causing us a huge problem. Matter of fact, I was the one who pointed it out to the MVCA saying that this really can't be cut down. So once again, the guy was just simply building up the mound. And this picture right here shows where the trees used to be, right along in here. The tape here is just simply showing the trees that still need to be cut. A lot of these trees in here will be cut eventually, or they might be already. This, believe it or not, improves our southern sky by about an hour's worth of observing. When I was out there, you know, you always do the old hand measurements, and it was about 15, 20 degrees. 15 degrees per hour at the equator, right? And so that gives us about another hour of observing time looking south. And that's pretty awesome. This is where we got a lot of the soil from for the mound. For those that know the area, there was a sand and gravel depository that was in here at one point, and we were given permission to remove a lot of this material. Over here, back on the mound, back over there, and back over this way too. What this inadvertently did for us, this gave us 25 to 30 more parking spaces. So eventually I would like to see something put up along in here to kind of cordon off the area so that people don't drive into the rocks that are still around here. But with this being said, you can start to see the possibility of having larger star parties at FLO. Something that we're just talking about right now. So that's what's been going on, and there's still lots of work that still needs to be done. Please see me if after the meeting if you'd like to help out. At least I'll take down your name. There's, like I said, there's still lots of work that needs to be done. When the topsoil comes in, we will need to level that out, pack it down, seed it either in the fall if it's early enough or in the spring. And eventually we'll be needing to put up some barriers as well. So at this point, are there any questions? Right here.
Where is it again?
Where's FLO? Yeah. Okay, Almont, Mill of Kintail. Do you know where the Mill of Kintail is? So picture the Mill of Kintail right here. There's, is it Concession Road 8 and Benny's Corners? It's on Benny's Corner. So basically the Mill of Kintail, if this is the mill, this is their whole property, it's on the Benny's Corner side. And there's a little gate there that says FLO. It's about this big or so. Black and white sign, or white and black sign. Yeah, 360 is it? 365. There we go. And if you're a member, you do not need to have a key access to access the site. There is a lock at the front of the entrance. That lock is the same combination as the key code to get into the warm room. Your membership gets you that. The observatory, that's a separate issue because there's some other equipment there that you absolutely need training on, and there's some equipment there that eventually needs to be replaced, so we'll be charging $25 per year for use of the observatory part. The warm room, you've got that as part of your annual fees. Okay? Question up here?
Yeah, there seems to be an awful lot of fairly tall trees all around. Now, does that not interfere with the observatory?
Here, let me block out some light here so I can see you. Do you see what I just did? Just so happens a lot of those trees are blocking out the light dome of Ottawa. So actually we asked them not to remove those trees. And these are hybrid, they're not white spruce, but it's a hybrid of white spruce. They're almost at their maximum height right now, so they're not going to be growing much taller. And like I remember in 1982, I helped them plant those trees when they were this tall. And Ross Ferguson is our contact at the Conservation Authority. When I met with him last year, we just went like, what were we thinking? There was a reason for it. There was no light bylaws in the area, so all the farmhouses around had their bright lights basically pointing right at the observatory because they didn't like us very much. So we planted those trees to block out the lights and didn't think too far ahead with that. So any further questions? Going once, twice, thrice. Okay, one last thing I have to say is, I mentioned this before, there's a $25 key fee, $30 key fee for the observatory. And that's payable to Oscar, and perhaps I'll let Oscar just mention the routine with that. It's for the entire year, and since we're just starting up our financial year, now's a really good time to do that. You have to be trained, and you have to be okayed by Rick Scholes or myself before you can purchase a key. So, thank you very much. If there's any questions, you can see me after the meeting. Thank you.
Thank you, Dave, for that update. Yeah, so the key fees are going to be they're prorated this year, just because we're trying to line it up with the club's fiscal year. So it's $25 this year. Going forward, it'll be $30. You can get cash or a check to myself. Checks can be written to the RASC Ottawa Centre, or you can e-transfer money to us at treasurer@ottawa.rac.ca. All right, thank you again for that update, Dave. All right, Paul is going to talk to us about his Dragon Quest.
Thanks, Austin.
10 standard minutes.
10 standard minutes. Oh, I see you brought the hook too. Okay. I'll try to be short. I'll try. You know me. Okay, Chris, actually, if I can get you to kill the lights overhead if possible. Some of the stuff I'm going to show is pretty dim and I don't need the lights up here. So, my Dragon Quest. This is a project I've been working on for over a year. It's a really interesting object, and an earlier observation that I showed you a couple of years ago kind of spurred me on with this, but I'll just dive right into it since I have about 9.5 minutes left. So, Dragon Quest, what's the dragon? The dragon. All right. That's the dragon. So the dragon is a really interesting galaxy. It is a gravitationally lensed galaxy that lies over halfway across the universe. It's about 7.5 billion light years from Earth. And this is a recent Hubble Space Telescope image of the dragon. The dragon is very shy. You have to really work at it if you want to observe it. So, needless to say, I was up for the challenge. How does gravitational lensing work? Gravitational lensing is a phenomenon predicted by Einstein's relativity, wherein the presence of any matter actually contorts or bends the shape of the space within which it's lying. It bends the shape of space-time. And so with gravitational lensing, if you have a very massive object at the center, and you're here on Earth observing, anything in that direction will have the shape of space bent slightly around that mass. That mass could be like a black hole, or it can be a very massive structure like a cluster of galaxies. And these gravitationally lensed galaxies that we see, black holes are small objects, so they don't really give us much in the way of looking at gravitational lensing phenomenon. We have to rely on very massive galaxy clusters to do that. So the dragon is one of the best examples of gravitational lensing. It's actually the first galaxy identified as such, and it was only discovered on deep photographs from large telescopes back in 1987. So it hasn't been known for all that long, but it's a really, really interesting object because what it is, and I'll talk a bit more about these other guys in a minute. What it is a single galaxy behind a massive galaxy cluster, and the shape of that space around the galaxy cluster has distorted the space in such a way that this is actually one galaxy, and there are multiple images of it. So if you're wondering how that works, picture like a funhouse mirror, or looking through a light through the stem of a glass or something like that. You'll see the light, but it'll be distorted, it'll be warped. And depending on the mass distribution of the galaxy cluster, that will determine the shape of this naturally occurring lens or telescope. It's actually nature's telescope. So this is actually one galaxy, and there are 5 images of it projected by this gravitational lens, forming one massive structure. So one galaxy. And these points that I've identified here, they're points where they've done the analysis on this image, and they see that those points are actually the same part of that one galaxy image. So really unusual creation, this thing. So you need a good, hefty galaxy cluster to be able to warp space to that degree, to give you this magnified and distorted view of these very, very distant galaxies. And these galaxy clusters are pretty common in space. They're everywhere. This is a Hubble image of the Centaurus galaxy cluster, about 170 million light years distance. And in the past, over the last number of years, I've shown you some of the galaxy clusters that I photographed. As I say, they come at various different distances. The Hercules cluster at 500 million light years out, and the Corona Borealis galaxy cluster at 1 billion light years from Earth. So these are very distant objects. And together, these galaxy clusters and the dark matter that envelops them all form this web of galaxies that permeates our universe. It's really kind of the large-scale structure of our universe, is these strands of galaxies with knots of these galaxy clusters at various points. That's a 3-dimensional representation of what our universe looks like on that scale. So the Dragon lives in Able 370, and this is an extremely far away galaxy cluster, 4.2 billion light years from Earth, or about 1/3 of the way across the universe. It was the last, or the furthest of the galaxy clusters cataloged by Able back in the middle of the last century, and it's 370 is, well, you can see the arc right there. There's the Dragon living in Able 370. So it's a large cluster. It's heavy. It contains hundreds, if not thousands, of galaxies packed into what is relatively a small area of space, if anything on this scale can be considered small. And so a couple of years ago, if I can go back there. There we go. A couple of years ago, I showed you a project that I took on because I've always been curious about these gravitational lenses since they were discovered. A couple of years ago, I showed you a picture of Able 2218. This is not my picture. This is obviously Hubble. And you can see the effects of the gravitational lensing. All of these curvatures, these streaks, are all galaxies much further behind the actual galaxy cluster. But their images are, their light is being refocused, repositioned, so it's magnified, but it's distorted, and it produces these rings, these arcs of distorted light. But very, very distant. Those galaxies, we can see them in images like this, but if you took away that galaxy cluster, they would be too far for even the Hubble to image. They would be extremely faint. This is, as I say, this is nature's telescope. So a couple of years ago, I took on this project to see what I could do with my 11-inch telescope. And you can see the Hubble image here on the left. And I was actually able to bag 3 of the gravitationally lensed galaxies, there, there, and there, corresponding to those guys. Because I really want to see what I could do with the equipment that I have under the skies that we have. And as you know, especially in the last month, they haven't been all that great. But even when they are good, the seeing is certainly not conducive to doing really high-res stuff most of the time. We have the jet stream over us a lot of the time, and it just mucks up the sky. Anyway, it took me, I had to do an 11-hour exposure to get those arcs. And I was pretty happy with that. But never being satisfied, I thought, okay, so what else can I look? I want to find out what the limit of my equipment really is. And I found with 11 hours, I could get these arcs, but I could also go deeper because you could see there are some very faint galaxies. and just to give you an idea, these galaxies, like these two guys here, they're 18th and 19th magnitude galaxies. They're not very bright at all. So Able 307, or 370, sorry, I got that wrong, provided a really unique challenge, because here's Able 2218, the one that I imaged a couple of years ago, and it's 2.3 billion light years from Earth. The galaxies that I was able to image are much, much farther away. You can see these distances. They're well over halfway across the universe, 3/4 of the way across, and no chance I'd ever see these without the gravitational lensing provided by this galaxy cluster. On the other hand, this galaxy cluster is twice as far away, which means that if the galaxies are comparable in size and brightness, now you're looking at galaxies that are only a quarter as bright, or about a magnitude and a half dimmer. This is a real challenge, because right now, with that type of dimness, you're looking at galaxies that are just above our noise floor, the noise floor being your instrument noise, plus, more significantly, the brightness of the background sky. So I'm fortunate I live in under a pretty dark sky when we have clear nights, and so I can typically get down to 21.6, 21.7 when I'm lucky on the magnitude scale. So it's pretty dark, but these galaxies are just above that noise floor. So in terms of the Dragon, oops, go back there. So in terms of the Dragon, what we've got is this galaxy cluster at 4.3 billion light years. The Dragon itself is almost twice as far, at 7.5 billion light years from Earth. So to try to image this thing, well, this is where it is. This lives in the throat of Cetus, a dragon living in the throat of a sea monster. Interesting. So I'll zoom in a little bit, because this is a really kind of a remote corner of the universe. Saw the area there. So this is a wider field view, and you can see this is not a very distinctive part of the sky. There's really not much in this other than a few bright stars in Cetus. We've got M77 not too far away from the target. So to see, or to try to see the Able cluster, we've got to zoom in even tighter to that port. And there it is. So this is my image of the Able galaxy cluster. And to get this image, I had to image 25 hours. So it's a 25-hour exposure comprised of 100 different frames that I had to stack. And through some digital magic here, I can provide you with a kind of a unique observation of this, because I can also subtract the stars. All the stars that you see here, they're all foreground stars in our own Milky Way. I've got to look through what's left of our Milky Way out towards the edge here, so I can see what's in deep space. But I can subtract those stars and give you an idea of what the actual cluster looks like a third of the way across the universe. So that's the Able cluster itself, and everything you see here, every point of light here is a galaxy. There's no stars left in this image. So this is very, very distant. And as I say, these galaxies are just above the noise floor for my particular conditions and equipment. These three bright objects here are also galaxies. I'm not sure if they're part of the actual Able cluster. They're certainly foreground to us. They're much closer. Well, they're certainly closer than the farther ones. So they may just be foreground in the same kind of line of sight. I'm not sure about that. I couldn't find the data on that. But that is the Able cluster. Now I'm going to zoom in a little bit more, because I want to show you a comparison of something. We'll just zoom in a little bit more. So there's my image of it, and you can see I actually did catch the Dragon. There's the Dragon there. So what I want to show you is, and I'm glad the projector is acting nicely here, because you can see there's a lot of little faint smudges all around. Now, some of that is a bit of noise from the sky floor. As I say, these things are just above the sky floor. It really drove me nuts trying to process this thing. But you can see the faintness here, and I'm going to show you. There's the Dragon. Now, I've just overlaid a picture taken by the Canada-France-Hawaii telescope, taken back in the mid-90s. So this was before Hubble took its image, and that's a superb telescope. I mean, I'm imaging with an 11-inch Edge HD. This is a 140-inch telescope on Mauna Kea. I need a bigger scope, man. But you can see it also captured the dragon very nicely, actually, and a couple of other of the arcs around there. But what's also happened is since that spurred a number of studies of this and other gravitationally arced galaxies. And so they turned the Hubble on it, and that's the latest of the Hubble images. Hubble has actually imaged this twice now. Back in 2009, so about 10 years ago, as part of the legacy observation, or the Final Frontier observations. And now they've just started a new program where it's called Buffalo, which is Beyond Ultra Deep Field Final Frontier Legacy Observations. Buffalo is easier. But what they've dedicated as part of this program is 100 orbits of the scope, 150 hours of imaging to image 6 of these gravitationally lensing galaxy clusters. And Able 370 is the first one of the target. They just finished. This image is just from about a month and a half ago. I didn't find the data for this, but its previous image was a 6-hour exposure. So it's not taking quick snaps of this either. These galaxies are a long, long way out, and they're pretty faint. They're pretty faint. But so you can see here, there's a lot of small galaxies here, and I'm going to flip this back and forth a few times. And you can see there's a good correspondence, certainly with some of the fainter ones. And we're talking, these galaxies are like 20, magnitude 20, I'm pushing 21. Really, really faint stuff. Whoops. There we go. So, yeah, I was successful with that, and I think I've discovered the limits of my equipment, certainly pushing even deeper exposures there. These galaxies I wouldn't get much more traction on that because, as I say, they're just above the noise floor. I could only use images that I got on the best nights to capture this, and certainly my telescope isn't in orbit. But you can see there's a lot of cool stuff here. But I'm going to close off with something I wanted to show you. They did this image with the Hubble of this galaxy cluster. As I say, I just finished this about a month and a half ago. And that picture there, I used this for scale to show the same scale as the image I was capturing. It doesn't do that justice. So I'm going to close off with a movie that NASA released, which is in high def, and it basically zooms across the diagonal of this picture. So, Chris, if we can roll that.
Just advance the slide.
Okay. One more time?
Yeah, advance.
Now check this out. This blows me away. You can see so many of the arcs here, and there's the dragon. So all those arcs are much more distant galaxies like the dragon, their light being magnified and also distorted by the sheer gravitational mass of this galaxy cluster. Here we go. I got to get a bigger scope. Thank you very much.
Thank you, Paul. And you came close to your 10 minutes. You only took 16 and a half. I can only imagine that it was the gravitational field from that cluster that distorted time.
Look at the galaxies I was close to. My time is moving way slower.
Thanks so much. That was really cool imaging, especially for a land-based 11-inch telescope. Crazy.
Guys. Yeah.
Yep.
Thank you.
All right. Moving along here. I guess we're heading to the break, but just a reminder, we've got tickets for sale for the annual dinner happening, I think the dinner's on November 30th at Algonquin College. We're having Professor Jan Kami giving us a talk there. Mike, can you remind me what the talk is about?
Search for life elsewhere.
Search for life elsewhere. Interesting topic. I can sell you tickets. We accept cash, credit, or debit now. We're also selling our 2019 Observers calendars, $16 for one, $30 for two, or $15 for any above one. Same deal, credit, cash, or debit. All right, so we'll go to the break. It's 8:15 here, so we'll take a 15-minute break. We'll have door prize tickets. If I can get a victim there to hand out the door prize tickets. And we'll see you back after the break. All right. I think the mics might be off. There we go. All right, welcome back. We're going to be having a special guest tonight, Benjamin Gerard, who's a PhD student from the University of Victoria. I believe it was last month I actually got an email, I had an email exchange with him. He was asking me sort of what the average seeing is in this part of the world, and I told him right away it's terrible, but but I tried to get a little bit of data for him, and anyhow, out of that, we got a really interesting talk tonight on imaging worlds beyond our solar system. I'll give Ben a warm welcome there.
Yeah, thanks very much. Can everyone hear me okay? Speak a little closer to the microphone. Yeah, so this seemed like a pretty good opportunity. Like Oscar said, I'm a... Yeah, I don't know if I speak louder, is this better? Yeah, all right. Yeah. So yeah, I'm a PhD student at UVic. As part of my program, I do a 4-month internship at a company in industry. So I'm spending the fall here working at Honeywell Aerospace. It used to be called ComDev. The smaller Honeywell, but they do a lot of projects with astronomy telescopes and astronomy-related things. So maybe, I think somebody told me that Alan Scott maybe used to be part of RASC or involved. Still is, great. Yeah, this seemed like a pretty good opportunity. So I'm going to talk about my PhD research on looking at other worlds. So here's an image of other worlds beyond our solar system. These are 4 massive exoplanets or extrasolar planets. They're all about 5 to 8 times the mass of Jupiter, so more massive than anything in our own solar system. And that blue circle is 10 AU. That's the orbit of Saturn. So these are all more massive and further out than any of the Jovian planets in our own solar system. Not, doesn't seem intuitive to form in our own solar system, but other different systems are out there. But this is a real image. This is not an animation or an artist's rendering. These are light from real planets. And so apart from just making pretty pictures, we can also do some very interesting science with these images. So here's another planet. They're all labeled a lowercase letter after the name of the star. So the star is 51 Eridani, and this is 51 Eridani b. So you can see the planet there. With the light from the planet separated from the light from the star, you can put that light into a spectrograph. So now, all of these images on the left are different wavelengths or colors of light. These are the different wavelengths. The movie is going through each wavelength here. And the planet, which is right here, gets brighter and dimmer as a function of wavelength or color of light. You can see the corresponding brightness that matches with the frame of the movie. So this is kind of interesting. Why would it do that? What is causing the planet to get brighter and dimmer like that? So here's where that movie started, and here's where the movie ended. This is the brightness of the planet. This, overlaid, is the brightness of Jupiter on those same wavelengths or colors of light. And interestingly enough, there's this dip right around 1.6 or 1.7 microns that we know in Jupiter, because we've sent probes there, is a result of methane absorption in the atmosphere. There are specific bands where methane absorbs a lot of light. And so even though we can't send probes to these other planets much further away, we can then infer that these other planets are in some way like Jupiter. They have methane in their atmospheres. So that's pretty unique. But there aren't a lot of these planets. That image that I showed is one of only a few. And if you bear with me until the end of the talk, I'll show a few more. But most of the effort in the field of exoplanet imaging is on how to actually get those images. It's a very technically challenging feat to actually take one of those images, and involves a lot of steps. So that's most of my research is not on the science of spectroscopy of exoplanets, for example, like I showed. It's on the technical development in improving the quality of the images to take those images in the first place. So the main challenge is contrast, which I'll get to, being able to see the planet under the glare of the host star. A first challenge is resolution as well, being able to resolve the planet separate from the host star. And I'll also discuss some of the instruments that I work with and instruments in the future that will potentially be able to see more planets and improve performance better. Okay, so this is an animation of a technique called adaptive optics, where on large telescopes on the ground, we can remove the effect of turbulence in the atmosphere and effectively make it seem as though this ground telescope was in space. So this is zooming in on the back of a 10-meter telescope, the Gemini telescope on Mauna Kea. And we're going to look into one of the instruments on the back of the telescope and see what's going on. How can we cancel atmospheric turbulence, removing that effect, effectively making it a 10-meter space telescope. So here's the light going to the camera, but also being split off to a separate sensor, which is open and not correcting anything. This is an open switch, and that light is all bouncing around because of the seeing that many of us know about from regular observations. So this is the sort of distortions from the atmosphere bouncing off this mirror and then going to the camera here, but this separate sensor measures those distortions and then closes the switch and sends that information to a mirror that can deform. It's called a deformable mirror. It can change shape every millisecond in real time to compensate for those distortions, which are then corrected here and sent to the camera. So this is open loop, and this is closed loop. And you can see, once that switch is closed, that effectively you're in space. So that went through pretty fast. Normally I try and pause the movie, but I'm not able to. Are there any questions, or should I play that movie again? Yes, please feel free to ask any questions. I don't want to go too fast or seem too overwhelming. Yes?
How does the mirror change shape so quickly?
Yeah. So there are a couple of different types of deformable mirrors now, but the oldest type that's been very well tested now, it's a very thin layer of glass that's coated with aluminum, but the way that it can deform is with a Tesla coil, a coil of electric wire that when you send a current through that wire or apply a voltage, there's a magnet below the coil, and the current creates a magnetic force in the opposite, equal magnetic force, so they repel, and that pushes the actuator up, or opposite magnetic force, and they attract it and it pushes it down. So it's using magnets.
So there's a bunch of them around.
Yes, when adaptive optics first started being used by astronomers in the 1990s, there were maybe about 10 of them on a mirror. Maybe the size of like 10 centimeters or something. Now they're as dense as about 1,000 of them on the size of like a penny. That's just the evolution of the technology. Yes, yeah, back there.
How do you know what's the correct shape of the mirror?
Yeah. So that's a good question. I guess this will sort of go through. I can't speed up or anything, but that separate part that split off into that sensor that made the sort of measurement and then closed the switch towards the mirror is called a wavefront sensor, and it's a way of measuring atmospheric turbulence. There's a number of different types of wavefront sensors, and the simplest one is called a Shack-Hartman wavefront sensor. It uses a technology called a lens-lit array.
Get your lapel mic, maybe that way you can.
Okay.
It'll be easier for you.
Easier to hear.
Yeah. So just clip that into your belt and then that one on your chest.
Yeah. So you see that's the wavefront sensor right there. So yeah, it looks sort of like a box, and that's because there's a number of different types of wavefront sensors. But
How close can you come to the Hubble Space Telescope in resolution?
yeah, I'm going to get there in a moment. It's actually better than the Hubble Space Telescope by a factor of 5, because it's 5 times larger. 10 meters on the ground, the Hubble Space Telescope is 2.4 meters. I was saying a lens-lit array, some people may be familiar with lens-lit arrays. They're used on some cameras just to focus more light onto the pixels. It's just a grid of lenses that can basically sharpen, make the CCD more efficient. And that same technology is used to measure distortion in the atmosphere. All right, so yeah, answering that question there, this is 3 images of Neptune. On the left, with a 10-meter telescope, the Keck telescope, or it could also be the Gemini telescope on Mauna Kea, without adaptive optics. So there's not very good resolution here compared to the others, because atmospheric turbulence is blurring out the image. The seeing in the image is maybe about 1 arcsecond on Mauna Kea. This is an image of Neptune with the Hubble Space Telescope. There's no atmospheric turbulence. You don't have to worry about that, but this is a 2.4-meter telescope. This is an image of Neptune with adaptive optics with a 10-meter telescope. So you can just make the comparison of left to right. The resolution in this image is about 5 times better. That's not the same as sensitivity to very dim objects like we were hearing about before. The background on the ground, the sky background, is much, much brighter. You can't go, with adaptive optics, because of how fast you need to run, you can't go beyond about 12th magnitude in the visible. Just for any imaging, you typically can't go beyond, 21st or the early 20 magnitude objects. With the Hubble Space Telescope, you can go out to 30th magnitude, if you can just integrate forever. So it's not to say that it's better in every aspect, but in resolution, the principle is that with a bigger telescope, for small areas on the sky, you can resolve finer detail. And why that matters very much in exoplanet imaging is that you imagine you take your two fingers, one finger is a planet and the other is a star, and you just bring those further and further away from your eye, they start to sort of merge together. Your resolving ability to tell the difference between those fingers, you know, if I go all the way across the room, isn't very good. And so with a bigger telescope or bigger eye to resolve that small angular scale, you're basically, you know, that's analogous to being able to see exoplanets further away. And believe it or not, with a 10-meter telescope, the farthest you can, you can only really look for planets on solar system scales within about 100 parsecs, or 300 light years. That's like 1% of the galaxy. So, you know, we were talking about going to the edges of the universe. This is the opposite of that. We can only look in the extremely local Milky Way for planets limited fundamentally by resolution, the size of the telescope. All right, the second issue is contrast. Does anyone know what this is an image of? The sun. What's this? What are these things? What part of the sun? Corona, yeah. So, and what about the instrument being used to create this image? Soho. Like, how about the piece of equipment on the Soho telescope? Coronagraph. Okay, that's what I was looking for. So, a coronagraph was first used in the 1930s, or invented in the 1930s by Bernard and Leo to observe the solar corona. And now we use this same technology for exoplanets. It's the same principle. You want to block out the light from the star to see the faint planet that is obscured otherwise without a coronagraph. So we wouldn't be able to see the corona, even though it's further away, because the photosphere has such a bright glare, and we don't have the contrast to be able to see it. So I think this is next a movie that will go through the concept of a coronagraph and how it's used on exoplanets.
This exoplanet in the distant solar system appears to have features very similar to our own Earth. It has continents, oceans, and clouds. This star has another planet. This one appears to be a gas giant not unlike Jupiter in our own solar system. As we move further away, the two planets disappear into the glare of their sun. The star now looks like all the other stars in the night sky. How will we ever see these planets? We cannot yet travel there, for the distances to even the closest stars are well beyond humanity's current capability to traverse in our lifetimes. We will have to rely on a space telescope. Housed inside this telescope is a science instrument called a coronagraph that is designed to separate starlight from reflected planet light. As the light makes its way to the coronagraph, we also notice signs of small distortions picked up when the light reflected off the tiniest of imperfections in the telescope's large mirrors. With the coronagraph not yet activated, we see on the monitor what the star looks like through a telescope. No matter how large and perfect the telescope is, it turns what was once a point of light in space into a round disk surrounded by concentric rings, the effect of what is known as diffraction. Somewhere behind the rings of light are the two faint planets. As you're about to see, a coronagraph helps directly image faint planets by doing three things. First, a coronagraph blocks most of the incoming starlight using a mask with a dark central region. The mask is carefully designed to redirect the starlight that it does not block off to the edges of the beam. As we see on the monitor, the inserted mask has already decreased much of the central starlight. Secondly, a coronagraph removes the effects of diffraction. When something that looks like a washer is placed into the light path, it blocks the light in the edges of the beam, and the rings disappear. We have now managed to remove almost all of the starlight, and are now able to view objects more than 1 million times fainter than the star. But what happens to the light from a planet? Why doesn't it also get blocked by the mask? Because the telescope is pointing directly at the star, the planet's light comes in at an angle, misses the mask, and passes through the center of the washer. But we are still unable to see the planets. If we look closely at the monitor, when we turn up the image signal by collecting more light, what appears to have been a blank field actually consists of blobs of leftover starlight. This scattered light, due to minute imperfections in the telescope's optics, is still hiding the faint planets. So this takes us to the third and last element of the chronograph, the removal of these scattered blobs. A special mirror is used with hundreds of tiny pistons behind it that can change its shape so as to correct the distortions in the light beam. As the mirror deforms, the blobs of light, as seen on the monitor, slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now start to see objects more than 1 billion times fainter than the star. Deep within the glare of their star, we have discovered our two planets. And if the light from these is passed through a prism, we will see the light spread out into rainbows of color. But when looking closely, some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So, a coronagraph. Reviewing the video, there's two main components. This occulting mask to block out the center of the star, but this doesn't remove these diffraction effects that they explain. So there are these concentric rings that go around the star, and if you just block out the center, you don't change those concentric rings. And so a planet, lying right on top of one of those bright rings called an airy ring is still too dim. So this second mask or filter called a leostop improves the contrast outside of the center of the star. It filters the image optically. This is an optical filter to improve contrast in the image to make it easier to see the planet. And then that light goes onto a camera or into a spectrograph through a prism, like they said in the movie, where you have this high contrast image. So this whole field is called high contrast imaging for that reason. And then, this additional part that they described in the video, which I call wavefront control. The wavefront of light is aberrated now. Let's assume we have a perfect adaptive optics system, or we're in space, so there's no more problems from the atmosphere. But when we take an exposure for long enough to collect enough light, this is what a coronagraphic diffraction-limited image looks like. These aberrations are no longer from the atmosphere. They're from polishing airs of the optics themselves. So a lens will focus light, but it's not a perfect lens. And the imperfections look like this in a coronagraphic image. These imperfections are there in a non-coronagraphic image, but they're at such a low contrast that you don't see them unless you're imaging with a coronagraph in the first place. So it's only in this high contrast case where we really start to worry about these problems. How are we going to remove these aberrations because we still can't see the planet? And so one technique that is actually part of my field of research is to remove these aberrations with that same deformable mirror that we used in adaptive optics. So this is light. We're dealing with waves of light, and we can create destructive interference of the starlight without removing the planet light in some part of the image to create an image that looks like this. So in this region of the image, the contrast is much, much better. We've destructively interfered those optics of the telescope itself using the deformable mirror to create this image.
And sorry, how do you measure it? With shine format?
Yes. So this is now a different technique because this is a coronagraphic image. So a typical shock carbon wavefront sensor measures in a collimated beam of light. This is on a camera in the focus, in the focal plane. And so this is actually a whole new field of research called focal plane wavefront sensing or focal plane wavefront control. And there's not one single way. A lot of people use various iterative methods. You can imagine, let's say, I have this many actuators on my deformable mirror. I'm just going to poke this one this way and then poke it this way and see if the image gets any better. And sort of iteratively converge until the image gets the best that it can. Yes. A whole field of research that the NASA movie did not go through because they're interested mostly in space telescopes, and this technique is more for ground-based astronomy, is differential imaging. So now there's no a deformable mirror is used for conventional adaptive optics, but instead of using it to subtract static aberration, we can just use an algorithm on our computer, on any laptop computer. So here, this is the coronagraphic image at a single timestamp, and it's rotating because of the way the observing is set up. So it's basically the rotation of Earth. Normally, when you're observing, you have a rotator mount. On an equatorial telescope, it will track in rotation. On an altitude azimuth telescope, you have to have a rotator in the telescope to move the whole field as the Earth rotates. And so this rotator is turned off, and that effect shows the entire telescope optics to rotate. And you can actually, this is HRE 799, that system with 4 planets. You can see in this coronagraphic image at least one of the planets there. You sort of have the contrast, but you can see all this static aberration that's still left over. What's done with this pattern of images is it's used to construct a sort of master calibrated image of all the aberration without the planets. And that calibrated image is subtracted from every one of these images to create every one of these images. It's just a combination of image and then a difference. That's why it's called differential imaging. And then all of these images are combined or stacked over time. So here's the cumulative integration time right here to create this image that you can see, especially close to the coronagraph, is clearly improving with time. So this inner planet here, there's no way you can see that here, and I don't think you can see that here either, but as the integration time increases, you can definitely see it on the right. And this is pretty cool. This just uses a certain observing mode of the telescope. You record the images, and then you just do differences on your laptop computer. You don't need a powerful computer or a fancy deformable mirror to do this.
What is that object over there? This one there?
Sorry, that's also a planet. Remember the first image that I showed that had 4 massive planets around a single star? This is the same system, HRD 799. The 4th planet, so there's 1, 2, 3, is actually, I think, over here. It's outside of the field of view of this image. All right, so at this point, I'm going to show this very complicated diagram, and I think I've explained all of the components in this diagram. If I showed this at the beginning of the talk, everyone would probably just leave. But now, this is the sort of stepping, progress towards imaging an exoplanet. The first light coming from the telescope, the first step is to do adaptive optics. There are 2 deformable mirrors in this Gemini planet imager. This is the instrument that I work with mostly, and a wavefront sensor that, like I was saying before, is a Shack-Hartman wavefront sensor. So this unit here measures the atmospheric turbulence and corrects for it, effectively creating a 10-meter space telescope for very small spatial scales. All right, so then you can see this light here is split off and goes towards the wavefront sensor, but then once this loop is closed and it's constantly correcting for the turbulence, the corrected light continues downstream into the coronagraph system. The coronagraph system blocks out the center of the star with this occulting mask and has this washer-shaped object called a leostop, or Leo mask, like we saw in the video, that improves diffraction in the image without blocking the light from the planet. This unit in the instrument, the calibration unit, or calibration system, is a separate type of wavefront sensor to measure and subtract the static aberration in the instrument, this imperfections in the polishing of the optics that then sends the information back to these same two deformable mirrors to correct the aberration that way. Differential imaging is not on this diagram because that's all just done on a computer. You don't need any hardware to do that. And lastly is the spectrograph. I haven't explained the integral field spectrograph yet. The short summary is that it's a prism, but early on I showed a bunch of images as a function of wavelength. And so this is actually what a raw image on an integral field spectrograph looks like. Does anyone recognize what object this is? Neptune. This is just like I showed before, but there's some sort of weird pattern throughout the whole images. So if I just zoom in to one part of the image, now you can get a better idea of what this looks like. Every single one of these lines is a spectrum. So what's going on here? A lenslet array, the same piece of technology that is a grid of lenses that splits up all of the light, is placed at focus, and then after that, a prism is placed downstream of this lenslet array to disperse the light in a wavelength direction. So all of the light here is sampled into these finite subapertures or microspectra based on the number of lenses on this lenslet array, and then dispersed because of a prism. So I can zoom in even further, and you can see this red grid is the x and y dimension of spatial x and y. This green line is the spectral direction. So now you can imagine this isn't, the images I showed before are processed. They require data processing to create those images as a function of wavelength. But you can imagine taking this red grid and moving it down a pixel, the entire grid, and then you're at another wavelength. Then moving it down another pixel, and then you're at another wavelength. And you can actually see, this is of Neptune, this is the wavelength direction. Here's a relatively brighter part. Here's a relatively dimmer part. You can, even in the raw images, see that there's spectral information from Neptune. Okay, well, any questions about an integral field spectrograph?
How many points are we seeing?
Yeah, there's like, I think something like 4,000 to 5,000 microspectra. Yeah, it's pretty.
It's a hypothetical question.
Sure.
Have this kind of technology incorporated on a moon-based telescope, basically on the dark side of the moon, relay stations to transfer the information back to Earth from the sunny side of the moon. What benefit would we have being that much closer to the solar systems?
Well, I would say, so you're in space, so there's not you don't have to have adaptive optics, but for exoplanet imaging, you still need a 10-meter telescope. You need the largest possible telescopes that you can build because of this resolution problem. So even with a spectrograph that looks like this, if we only have a 1 or less meter telescope on the moon, it'll be very, very difficult to bring large telescopes like that to the moon. That this whole image is just going to be blurred into like 2 resolution elements. And so the whole concept of high resolution imaging really relies on large telescopes. And so for the sort of near and distant future, I think that's limited to the ground. 10-meter space telescopes are coming in like 30 years. If people have heard of LUVOIR or LUVOIR is the current concept being studied by NASA, but that's coming in like 2030s or 40s. I don't think there's a launch date or anything.
See that happening before us going to Mars?
Perhaps we can take
No.
questions. Let's
Yeah.
take questions till
Okay,
after the end of
yeah.
the meeting. We're starting to run a little short on time.
All right, so this is, I'm mostly done here, a future telescope that Canada is heavily involved in, and specifically my research institute, the NRC in Victoria, is the 30-meter telescope, so that's a good segue. We are on the ground able to build larger telescopes. It's much cheaper. This is already like a tenth of the cost of the annual budget for the Hubble Space Telescope. But it requires a collaboration of all of these different countries. And at the moment, there's no exoplanet imaging instrument. That will come later. Mostly the efforts have just been how to make a telescope this big. So like the Keck telescope, if people are familiar, this uses a bunch of segments that are all phased together to effectively create a telescope that large. It's not a single monolithic piece of glass because after about 10 meters, that glass would just collapse on itself. But what is already finished with design, it passed the final design review this summer, is the adaptive object system for the 30-meter telescope called NEFARIOS, Narrow Field Infrared Adaptive Object System. And this was mainly designed at the institute where I work, NRC Hertzberg. It uses 2 deformable mirrors, and those same deformable mirrors will potentially be used for specifically a high contrast imaging instrument with a coronagraph and an integral field spectrograph in a later point, probably also towards the late 2020s, early 2030s. Okay, so everyone sort of, no one left, so now I can show the pretty images. So here's another system, HD 95086. They all just have serial numbers usually. Here's the initial detection of Planet B in 2013, and this image is with the Gemini Planet Imager, the instrument I work with, just 3 years later, and you can see just in a 3-year time span how the quality of the image has improved. The resolution, the inner working angle has improved a lot, and also the contrast in the image. So this sort of illustrates that this is a very new and rapidly evolving field because of the technology growth at a very fast expanding rate. This is Beta Pictoris B. This image is from 2002 or 2003, I believe. Very old. This was actually the first directly imaged exoplanet, but they thought it was a background star. They didn't think it was a planet, and it subsequently disappeared actually behind the star, and didn't realize it until 2010 when it popped back out on the other side of the star. So that's when they realized, oh, we actually imaged a planet. So that was very painful for them. They were just sort of waiting around. All right, and then here's the last slide. This is that same system, HR8799. This is the only multi-planet directly imaged system, and because this is such a benchmark famous system, it was detected in 2008 and has 8 years of imaging. This is a sequence of those 8 years of imaging compiled together, and this is probably the only movie in the world where you can see orbital motion of planets with your eyes. This is not a simulation. These are real images. So, pretty cool that this is possible now. Thanks very much.
So we can take, I can take maybe 2 questions, and then perhaps after the meeting, if Ben's still around,
Sure.
he'll take a couple more.
Yes.
Question about the short phase of contrast exposure. Sounds like we're trying to fix static imperfections in the mirror. Why do we need to measure them over and over again? Why don't we just program them with lots of measurements?
Well, so you're asking about why you need to constantly correct for them? Yeah, so these there's another effect that I didn't explain. So these aberrations are often referred to as quasi-static. They're not exactly static. The optics are, they're still there all the time, but because of a change in temperature, for example, and this is an observable effect on the Hubble Space Telescope. The HST actually has a coronagraph. It's not optimized for high contrast imaging, but you can do coronagraphic science. And what you see, for example, on the day and night side of the Earth when the HST is orbiting, is that focus changes by a very small amount that's usually negligible for non-high contrast science, but when you take a coronagraphic image and try and subtract out the static aberration on the beginning of the night orbit, because it was just, it's cooling off from the day side, it's at a different focal length than at the end of the night orbit. And so that's, one main reason why you need to sort of constantly measure the focus in real time. So that's focus, there's all sorts of higher order modes as well.
Okay, one last question.
Yeah.
Yeah, you said it's the same deformable errors that are at for both the atmospheric perturbation and the optics itself.
It can be. You can have a different one. There's no reason why you...
My question is that, how would one correction undo the good that was done by the first?
Yeah. So that's the nice thing about playing with light. So it's not like adding. You're adding the correction of the static aberration onto the correction of the atmosphere, but by canceling the atmosphere, you can imagine. It's hard to do this with my hand. Here's the atmosphere. This is creating, this sort of sine wave, and so to correct for it, you do this, and that creates this. That creates a, flat, unaberrated wave. And then on top of that, here maybe, smaller amplitude. Here's the static aberration of the lens, and so on top of, I think, this shape that you did before, you do, this. And so if you add, canceling the atmosphere with canceling the lens, that's going to cancel both of them. So you can just add the shape of the wavefront. It's not the same as what you see in the image. It's the sort of phase aberration. It's how that sort of, in that movie you saw these sort of planes of light going through the system, how that deviates from flatness. And if you measure that in either atmospheric turbulence or static aberration, or both at the same time, it's doing the same thing. You're improving the quality in the image.
All right, thanks very much, Ben. And that was a fascinating talk. All right, we're going to get to our observation reports here. So if you're up on this list, if you could just please line up to the side. So Jim, you're up first.
And the clicker's right there. Clicker's there? Yep. So this is the forward?
Yeah, forward, laser, back.
Forward, laser, back.
All right.
One more click there.
Okay. So a couple of months ago, I was at Calabogie, and I used the Malincam exterminator with my Celestron 8 Alt-Az mount to capture M51, which is a spiral galaxy in the constellation Canes Venatici. And as you could see, it's interacting with a dwarf galaxy, which is NGC 5195. Let's see, where is that one? Where is that light again?
The laser?
The
It's at
laser.
top left.
Oh, the laser right there. Okay. All right. Moving right along. Oh, by the way, M51 Another name for M51 is the Whirlpool Galaxy.
What was the exposure time, Dick?
This was 22 seconds. And the gain on that was 3. All right. So another dark site that I went to at Foymount, I used the same equipment to capture NGC 891, which is an edge-on unbarred spiral galaxy in the constellation Andromeda. And this galaxy is approximately 30 million light years away, and it was discovered by William Herschel in October 6th, 1784, and that must have been a clear night for him. And my last image, this is an image of M16, or the Eagle Nebula, which is in the constellation of Serpents. And the Eagle Nebula is actually composed of a star cluster, an emission nebula, composed of mostly hydrogen, and also a dark nebula, which is composed of dense molecular hydrogen, other gases, and dust. And the image, this image also contains the famed pillars of creation in the center, which is right there. Anyway, thank you very much.
Cool, thank you, Jim. All right, up next I think we have John Thompson.
Hi, this is a visual observation I made on the evening of October 20th. It was a Saturday night. I was at a concert downtown and driving home, and about halfway home, directly in front of me, there was a fireball, which was a very bright meteor which moves much slower than a typical meteor. That lasted about 3 seconds. So as soon as I got home, I wrote down all the details and then reported it to the American Meteor Organization through their website the next day. And you'll see that it's the highlighted line on that on that page. And it turns out that there were 4 other people that reported it. So when I first reported it, it went into a table called pending. And then 3 days later, it appeared, after they analyzed the data and cranked out the numbers, they regarded it as an event because it has 5 observations in this case. And it was seen from Quebec, Ontario, and from New Hampshire.
You can click on the right button.
So this is what they presented. Okay. So there was 1 observation from New Hampshire, 1 observation myself is from Ottawa, 2 from the Montreal area, and then 1 from Quebec City. And I think the Quebec City one might have been spurious because it gave a time of 15 minutes later than the rest of us, but I recorded 11:03, the others recorded 11:05. But I believe the lines indicate the length of the track in the sky. The people from Montreal area would have seen something very short but very bright. What I saw was longer, and then the person in New Hampshire would have seen it as even longer still. But I recorded about 3 seconds after analyzing the data. They called it 3.5 seconds.
Those are 3 slides.
Oh,
there.
is there a third one?
Yeah, I showed it intermittently
Oh.
there. You can go back though if you want to show it again. Just give it a second. It was the second slide there.
There's one more?
No, there's this one and then this one. There's just those. You sent 3 images to me there.
Oh, there it is, yeah. I found out several days later, if I put my mouse cursor over that circle, that little icon at the top left, the KML, it gets a little bit more data, which I've underlined at the bottom. They give the average start height of the track, the average end height, and the impact location. So I'm guessing those numbers are probably meters. So it started at a height of 80 kilometers. It flamed out at height of about 70.2 kilometers. And where it would have ended, it turned out it would be in the ocean somewhere between Labrador and Greenland. But it was a very shallow track that if you, the length of the track is that blue line. So it only fell 10 kilometers over 225, so that's an angle with respect to the horizon of only 2.5 degrees. So it was a very, very shallow, almost earth grazing event. And then there was one more thing I was able to figure out, that there's a table on, if you have the Observer's Handbook on page 253, if you have the brightness and the velocity, and I was able to obtain that from this information, you can actually estimate the size and mass of the particle. In this case, the particle would have been between 6 and 8 millimeters estimated, and about 5 grams. So that's the size of maybe a medium to large size pebble, because most meteors are just basically dust or grain or sand size particles, but fireball will be like a pebble size. And actually, I understand that there was probably some sidewalk observing going on that night. I was curious if anybody else had seen that fireball. It was just after 11 p.m. in the east. So anyways, I was one of 5 who recorded it. It's the first time I've actually submitted an observation like this, and it's interesting how much information can be obtained when you combine it with other observations from other people. In this case, there was another 4, total of 5 observations.
John, one of the Kingston Center members runs an all-sky camera
Okay.
all the time, and he did report seeing a fireball sometime in the past week or two. I'll follow up.
Yeah, this was the evening of October 20th, and it started near Trois-Rivières and ended north of Quebec City.
Yeah.
And it over that length, it would last about 3.5 seconds, and it only dropped 10 kilometers. Like it started at 80 kilometers and it finished at about 70 kilometers. But it probably kept on going, and if it survived the rest of the flight, it would have landed in the North Atlantic Ocean. Okay?
Yeah.
All right.
Thank you. All right, Rick. Just click one more time there.
Okay. So I just wanted to, well, good evening first. I wanted to show a couple of things I've done over the past couple of months. So the morning of September 15th, comet Giacobini-Zinner 21P, so it's a periodic comet, went through the open cluster M35. Now, it's an interesting comet. We had been watching it at the Fallen Stars Star Party as it was going along between, or near M36, and we kind of followed it across the sky, but then we looked and realized that on the morning of the 15th, it was going to go through M35. So that's the comet there. This is M35. This is NGC 2158, and that's IC 2157, another little open cluster. So these are both open clusters. This one just happens to be about 5 times as far away. So this was, I can't remember, 24 minutes, I think, with my 90 millimeter Apple refractor and a Canon 60DA. So, something happened in the sky at a specific time, and it was actually clear. That was really unusual.
Must have not been in Ottawa.
No, it wasn't in Ottawa. What was really interesting is the next morning, about 23 hours later, 24, 25 hours later, there was actually an occultation of a star by an asteroid. So, the asteroid Sappho, number 80, the 80th to be discovered, was discovered by Norman Pogson. We all remember Norm. He's the one who defined that a difference in 5 magnitudes is equal to a factor of exactly 100 in brightness. He was working in the observatory in Madras, India, discovered several asteroids, including this one. And every so often, these asteroids, this one's about 83 kilometers in diameter, based on radar data. And as it travels through the sky, it can actually go in front of a star. And so on the morning of the 16th, it was actually clear again for a timed event. And the star Hipparcos 24403 is a 7.2 magnitude star, was going to get this little 11.2 magnitude asteroid go right in front of it from my house. So what happens is, well, we'll start the video. So this is a video with basically a very high webcam. And you can see that the star just blink, disappears. The asteroid itself is too faint to show up. So let's see if we can do this again. So this is the star. This is very cropped in, so you can see great big pixels, and it was rather turbulent at the time. And this is again with the 90 millimeter Apple refractor, so it's not a lot of aperture, but it's a 7th magnitude star, so it worked well enough. And with the fire capture software, it actually timestamps every image. So I was able to get, this is shooting at about 50 frames a second. So with a resolution of about 0.02 seconds, I was able to time the start and the stop and report that to the International Occultation Timing Association. And the total duration was about 3.5 seconds. Later in October, normally I do photometry, measuring variable stars, and I rarely take the time away from that to do pretty pictures. But one evening, just before we were starting supper, I realized that none of my variable stars were doing anything exciting. I had 5 or 10 minutes to set the telescope up and get it imaging something before I went in for supper, so there was M27. So this is unfiltered. This is about an hour-and-a-half exposure with the 40 centimeter Boltwood telescope. So you can see in this image, this is sort of the dumbbell that we almost always see in any telescope. Some people call it the apple core, which I think is far more descriptive. And then, of course, there's the outer sort of rugby ball shape that you can see under dark skies and better conditions.
What camera are you using there, Rick?
That's my ST2000, S-Big ST2000. So, as I say, I do a lot of variable stars. This is variable star CSS, blah, 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 blah. It was detected by the Catalina real-time transient survey program, where they're looking for things that pop in the sky. And this is the star that I'm interested in. And they reported that it's an R-Lyrae star, so it's a pulsating star with about just over a quarter of a day period. If you look it up in the American Association of Variable Star Observers Variable Star Index, they report that it's called an RRD star, which is a double mode star. So it's actually pulsating in the fundamental mode and then also pulsating inside that in like an overtone frequency, so with 2 different frequencies. So clearly we don't know exactly what this star is doing. And these are very important stars because it turns out that because they're pulsating in both modes, we get a much better idea of what the physics is inside the star. So that's why I'm imaging it. I only started it in about the middle of September, so I've only taken 324 images of it so far. But somebody made a comment from the Kingston Center, and I had been noticing that there's 4 little galaxies in here. And so I checked in Earth-Centered Universe, and sure enough, there are PGC, Principal Galaxy Catalog, those 4 little galaxies. And they range from, I think, about 18.2 down to 18.8 in magnitude. No, that's it there, and this guy. Except, so I thought, well, I can overlay a bunch of these images. I've got lots. This is a single 5-minute exposure, and you can see that there are more smudges in there. So what I did was I took 224 of these images for a total of 19 hours of exposure, and you can start to see that, yes, indeed, there's a whole bunch. All these little fuzzy dots are all galaxies. It turns out there's a fairly good-sized galaxy cluster just out of the field of view above. So this is this one, this one, this one, and this one are the PGC galaxies. So I wanted to, my first thought was, well, I'm going to go through and just count the galaxies, except that, well, you can see there's a whole bunch more down here. Look at them all. So what I did was I used my normal photometry software, which basically goes through and measures the brightness and the size of all the objects in the field and tries to distinguish stars from galaxies. And so what it comes out to is there's actually about 425 galaxies in the field of view. And the very faintest ones, there's some little faint ones in here that you probably can't even see on the projector, but they're down about 22.6 magnitude. So that's the faintest. I haven't got the patience to do 19 hours of exposure on galaxies, but on my variable star, I'll do hundreds and hundreds of hours. So I may update this in the future.
What constellation was that in?
This is just up in the northeast side of the square of Pegasus. So, and I think that's it.
Cool. I get an inverse.
Oh, yes. Just an inverse image because it shows things up a little brighter. Good. Thanks.
Thank you, Rick. All right, I think I've got Pierre up next. Advance the slide there.
All right. Well, good evening. I found John's report quite interesting about the fireball because I wasn't out observing, but I remember being in my living room, just sitting there, and I saw the glow through the window. I didn't see the meteor, but I saw a glow that came in and out, and I immediately suspected there must have been a meteor, and then I was kicking myself for not being out observing. So anyway, earlier in October, I started watching for this meteor shower coming up, the Draconids. For those of you who know me, I've always been interested in meteor showers. It's my passion, following both the major and the minor meteor showers throughout the year. And I've always had, throughout most of my 26-year sort of career of meteor observing, I've always had this very, very curious interest in the Draconid meteor shower, which actually is a meteor shower caused by comet 21P, Giacobini-Zinner, the same comet that Rick presented on his nice image, overlapping M35. So that's where these meteors come from, little bits of dust and particles that enter the Earth's atmosphere and cause this meteor shower. So for 2018, there was initially a lot of excitement and interest for this year because the comet itself has just passed perihelion, and basically the Earth was going to be in the region of space that the comet was only 26 or so days after the comet itself. So basically, the odds were that, and then normally we would expect to have a meteor storm, something very spectacular. In the case of the Draconids, it's a very, very difficult meteor shower to catch most years. Nearly every year, you can expect to see just about 0 or maybe 1 meteor, maybe a couple in the whole night of viewing. In some rare years, like 1933 or 1946, we had some of the most intense meteor storms in the 20th century, where the rates shot up to 8,000 or up higher than that per hour. And in a handful of other years, the rates were, we had outbursts of several hundreds Draconids per hour. Whenever, the comet was close to perihelion and the Earth happened to pass through the thicker concentrations of dust that followed closely behind the comet. So 2018, this year, was one of those years because the comet just swung by and had a pretty close approach to the Earth. So unfortunately, the meteor dynamicists, when they looked at their models and they simulated the dust particles released from the comet throughout several past perihelions, they determined that this year the Earth would be going exactly in between two dust clouds. So like a gap, basically, in the orbit that was previously caused by previous encounters by the Earth causing this gap in the dust. So we were going to pass through this region. No meteor storms were predicted, but there was a good chance that there could still be some heightened activity, with a prediction calling for typically maybe about 15 per hour rates, maybe at best up to a few dozen. That was it. The good news with that is that for the Draconid peak, predicted evening of October 8th, it was new moon conditions, and it was also the peak time, which was highly favorable for eastern North America. For our longitude, predicted to happen right after sunset, right after the sun went down, after evening twilight, around 7:30 or 8 o'clock evening Eastern time, was the predicted outburst. So perfect for us, with a radiant very high up. So with the case of the Draconids, you don't have to wait until 4 a.m. to see them at their best. You can see them at their best as soon as it gets dark. That's the part that's kind of cool. So for 2018, of course, as we got closer and closer to the peak, I got concerned about the weather. Like, the weather really sucked for Ottawa. It looked like there was going to be a blanket of cloud, no chance, zero chance of any viewing for Ottawa. So what did I do? I decided to hop in a car, go for a road trip, go to where I could get to clear skies. And that was 1,200 kilometers to get to a place like that, 12-hour trip. So the best prospects was basically the state of Indiana going up towards Lake Erie. There was a large zone of high pressure that looked like it would be clear there. So I figured I'm going to go for it, because this could be the year I could see a significant Draconid outburst, something I've been wanting to see for many, many years. It's been one of those meteor observing goals I've been wanting to see. And I figured this was my shot. Even if it's just a minor activity, I figured, why not? I'm going to go for it and go for an adventure. So here I am. This is my setup. I drove all the way, gave myself 2 days to drive there to get to find a place that was a state park, safety, and also with reasonably dark skies, which I found is not all that easy in the state of Indiana. There's a lot of light pollution, a lot of cities, and I think because the general geography, it's pretty flat land, is pretty flat space, so there's a lot of light pollution that just spreads out in all directions. But I found one place here that was now fairly dark, roughly in the yellow zone of light pollution map, so for me that was good enough to get a decent sky to try to see this. And I set up my cameras, kept it very simple, and then I started watching. As soon as the sun set, I started watching, and then I waited to see if something interesting would happen. Within only about 40 minutes after the sun went down, the sky was still blue. I could see Vega, I could see Arcturus. I saw my first Draconid, and then I knew, wow, maybe something's happening. And it was clearly a Draconid, very slow meteor. It looked like a teardrop that just went by. And that's what they look like. They're very, very slow meteors compared to the Perseids or even the Geminids. And then I saw another one, and a minute later, another one. And then I knew something pretty big was happening. So here is the result. There was a strong outburst, much bigger than what the predictions were calling for. The zenith hourly rate reached 150 at the peak. So this was a bit of a surprise for the meteor community, and pretty exciting, because for one time you had a meteor shower that actually performed better than expected. And for a period of about 3 hours, the rates were over 1 meter per minute. So between about 7 o'clock in the evening up until about 10 o'clock, we had some pretty strong rates happening. And then after 11 o'clock, near midnight, everything started declining, and then by midnight, it appeared there was basically nothing left. So it was actually a pretty long-lasting outburst compared to previous Draconid outbursts, which typically lasted only between half an hour or an hour at best. This one actually had a pretty long curve from start to end. And here's the result of one of my cameras. So this was the camera pointed straight at the radiant in Draco, and I was interested to capture everything that was coming out of that direction. So this is a 35 millimeter lens. It's a composite. So basically I've shot picture after picture, 20-second exposure, not guided, so they were short exposures. And I looked through all 1,500 images and found all the ones with meteors and stacked them, created this composite image for the outburst that occurred. So as you can see, just for reference, here's the constellations, just to give you a sense of where things are. And for the most part, this outburst, a lot of the draconids were on the faint side. They were very slow. A lot of them happened actually very near the radiant. And as it turned out, there's the traditional radiant is predicted to be about right here, near the head of Draco, but should be down here. For this outburst, the radiant was actually shifted by a few degrees up somewhere around here. So this is one thing that's currently under investigation to see. That means that the meteors came in from a slightly different direction, very slightly different direction in space from the comet. So another possibility is because these meteors are so slow moving at only about 20 kilometers per second, which is considered very slow for a meteor, that possibly the shift of the radiant up towards the zenith by a few degrees was caused by the deceleration of these meteoroids as they they came into the atmosphere. They might have had a slight arc that caused the direction, the angle, to change for the radiant. That's another possibility, but it's currently under investigation, and there's been a lot of Europeans who were successful in catching the draconids, whereas North America, not so much luck. I was one of the few with clear skies. A few people in the Maritimes were able to see the outburst very well. On the next shot, there's a close-up that we're going to zoom into this part, just to have a look at the very short meteors, the foreshortened meteors near the radiant, which is about right here. And this is the shortest one right here. I remember seeing it with the eye, and I was like, did I see a meteor? It just looked like a star that came in and out. That was one of them that came almost straight at us, head on. And look how interesting this is. The draconids are known to be very fragile meteoroids. They're fluffs of comet dust, but unusually fragile. So notice they typically get bright very early and they fragment. Sometimes they show little bursts or little flarings in the trails, which is fairly uncommon for slow-moving meteors. Typically would show just a very even in and out path, but these can be very interesting meteors. And although a lot of them were faint, there was also a few bright ones that occurred during the outburst. My second camera was aimed lower in the north. There's the Big Dipper right here, and you can see there's a good 34 meteors in this image composite that was running during the same time between 8 o'clock and midnight. And you see there's a lot of faint meteors all over the sky coming up from the radiant. And this one of the Draconid fireballs. There were not many, but there's the really good one that occurred as the sky was still very bright twilight. And look how cool it looks. The meteor started quite bright over here, and then as it descended, it started getting dimmer, and then there's definitely signs of fragmentation right here. There's several little brightness areas, and let's zoom in, have a better look at it. So this one I didn't see visually because it was kind of behind me over the trees, and I was facing very high up looking towards the radiant, so I never got a chance to see that meteor directly. So that's about it for my presentation. I'm going to keep this short because I think I'm just about out of time. But in the next couple of days, I'm going to post a full report on the Ottawa Astronomy Friends group and also on the OAOG. Have a look. You can read about this adventure, and also I'll post my pictures up so you can have a look. Thank you. All right.
All right, thank you. I think the last one is mine. So this is my image of the Sol Nebula. It's about it was 4 hours of exposure through a Skywatcher Equinox 80 ED using a Canon 60DA. So this is a H2 region in Cassiopeia. I think it's cataloged as Sharpless 2-199. I showed you guys the Heart Nebula last month, so figured I'd show the Soul Nebula this one. All right. Thank you. All right, time for the observing challenge. So last month, the challenges I'd put up were the M31 for the beginner challenge, NGC 6888 for the intermediate, Stefan's Quintet for the advanced challenge, and Mons Hadley and Rima Hadley for the lunar challenge. Did anyone try to do the challenges? I guess we didn't really have the weather for it last month, but this month we're going to go with the Helix Nebula for the beginner challenge, cataloged as NGC 7293. Planetary nebula in Aquarius. It's at 7.3 magnitude, and it's a good target for small scopes and binoculars. For our intermediate challenge, we'll use the Blue Snowball NGC 7662, which is a planetary nebula in Andromeda, 8.3 magnitude, and it's also cataloged as Caldwell 22. For our advanced challenge, we'll go with the NGC 51 group. It's a group of galaxies in Andromeda, ranging in brightness from 14.1 to 15.4 in magnitude. And it includes NGC 49, 48, and 51. Strange that I ordered it that way, but what can you do? IC 1534, 1535, and 1536. And our lunar challenge will be Plato's craterlets, which are 16 craterlets in the lunar crater of Plato. They range in size between 0.9 and 2.4 kilometers in diameter, and they're best viewed on lunar days 8 and 21. All right, so just a summary of the observing challenge for this month, and I hope I get some submissions. Photographs, visual observations, sketches, whatever works for you is more than welcome for observing reports. All right, FLO star parties. Looks like the last one we had was on the 13th of October, and it was a go. And then we've got our dates going forward, the next one being November 10th, weather permitting. I think we've closed off our free public star party season at the CARP library, but that's due to return in the spring. Oh, I'm wrong, apparently. We have more dates, 9th and 10th of November, with rain dates of the 16th, 17th. All right, Estelle's pick of the month is We Have No Idea, A Guide to the Unknown Universe. That sounds like a pretty interesting read. All right, and on November 13th, there's going to be a speaker named Howard Simcover, who's going to be giving a talk on Mars at the Central Experimental Farm, and that's brought to you by the OFNC. I believe it is, yeah, I think everyone's welcome. So it's Tuesday, November 13th, at 7 o'clock, it looks like, when things get started, and the presentation at 7:30. All right, club information. Here's some of the great folks that keep the club running. Just a quick clap for them. Our meetings are recorded and posted on our website. Keep an eye out for this month's meeting coming up. Our audience tonight, 105 speakers. Thank you all for coming, and thank you to all the organizers and speakers. If you have any ideas or comments, feel free to email me at meetingchair@ottawa.rasc.ca, and I'd just like to thank the museum for hosting us. All right, a post-meeting meeting will be at Grace O'Malley's as usual. Hope to see you guys there. And our next meeting is coming up on December 7th at 7:30 p.m. Just a reminder that about half an hour to 45 minutes of that will be for our AGM. All right, here are membership benefits for joining the club. You get access to the Ted Bean Loan Library, the Stan Mott Book Library, so you can take out that book of the month, as well as access to the Fred Lossing Observatory. You also get an assortment of publications, including Sky News and the Observer's Handbook. All right, and time for door prizes. Thank you, everyone. I'll just call out the last four numbers.